Well, all right, here we are. um, so I just want to mention a few things since we haven't actually done this yet this semester. I see you all have your microphones muted. That's good. If you want to ask a question, you can go ahead and unmute it. You should probably leave it muted for the time being because that way there's no background noise. And so, for example, if your dog starts barking or the little brothers start running around or something, we won't hear it. And then also, this is all being recorded. So if you want to watch it again later on, you certainly can. Anyone who's absent can watch it later on. So here's what we're going to do. We're ready for chapter 15, which is the last chapter in the course. The final exam will just be based on chapter 15. It's a fairly complex topic that we're about to look at, but it's also incredibly important. In fact, you'll see this quite often if you do any actual research or analysis of real world data. Chances are that there'll be regression and analysis involved somehow. Also, later on, I'll show you how to run one of these in Excel, just because it's important for you to understand how that works. And also, it gives us a lot of results that we can look at. But also, we'll be happy to know that is so often the case, your calculators will come in handy here too. As a matter of fact, as a rule of thumb, the more complicated something is that we are learning, usually the more help the calculator can provide to us, and this is no exception. So now, unlike the other chapters here, there is a fair amount of terminology that we have to learn and notation that we have to be introduced to. It's kind of different than what we've been doing. But ultimately, at the end, we'll be doing a lot of hypothesis testing. That never really stops. But what's different now is that what we're trying to do is take real world data and estimate relationships between different variables. We want to understand, for example, how much changes in interest rates affect the demand for new cars or something along those lines. And so this is one of the best ways to do that. This is a very broad topic. If you were in graduate school, you could take an entire semester just about regression analysis. In fact, more than just one. It's that complicated, but also that important. So here we're going to start with the basics. And what we're ultimately trying to do here is estimate the relationship between two variables that we assume have a linear relationship between them. All right, so let's get started. Let's see. First of all, what are we doing with regression analysis? We're using our sample data to estimate both the strength and the direction of the relationship between two or more variables. Now, for example, what if we wanted to understand, imagine you're in the marketing department of some major corporation and you're responsible for figuring out the optimal amount of advertising dollars you should spend to reach the maximum number of customers. So what we might want to know is, every time we spend one more dollar in advertising, how much does that bring in new revenues? Obviously, if you don't have that information, you're just guessing, and then you may potentially make very bad decisions. So that would be a classic example of when regression analysis could be very, very helpful. Not only that, but then once we have this information in place, we can use it to make forecasts. So once we, let's say, estimated this relationship, we could say, for example, if we spend $100 million in advertising next year, what is that likely to do to our sales revenues? So, forecasting is tricky business, but we have to have some mechanism for doing it properly. And one way to do that is to have a regression model that we can use to make predictions about the future. Now, it turns out there's two basic types of regression analysis, simple and multiple. We're not going to do multiple regression. There really isn't time, and it's much more complicated. But you should be aware that there is such a thing as multiple regression, where what's different between the two is that with simple regression, we're assuming that there's only a single dependent and independent variable. Now, there can only be one dependent variable, but for more complicated situations, we can have multiple independent variables. So, for example, what if we just sneak in a new example here? For example, we may want to know what happens to cells if we change both our advertising expenditures and we also change Oh, what else could we change? Our prices or something along those lines. So in other words, um, we are implicitly assuming here that sales depend on both advertising expenditures and prices. We can analyze this relationship with multiple regression analysis. Okay, so that's what multiple regression would be all about. Simple would mean we're assuming just the one independent variable. Okay, by the way, I almost forgot to mention, besides posting the video on, I'll try to get it on both Blackboard and on my YouTube account. I in the past I've had issues getting videos onto Blackboard. Sometimes I don't know, I guess there's memory issues and things like that. And just in case it doesn't work out, I know that YouTube works very well for this kind of thing. And so I just happen to have my own YouTube channel. I set it up during the COVID when all of our classes were online. You can see I've got millions and millions of classes here from over the years. So I will create a separate playlist just for us, so you can find our recording if you can't find it. Okay. All right. Anyway, but simple regression would mean that you only have the one independent variable. So you might say, for example, we're assuming that sales revenues only depend on advertising and nothing else. Okay. With simple regression, there is only one independent variable. For example, we may assume that sales revenues depend only on advertising revenues or advertising expenditures. We can analyze this relationship with simple regression. Now, you might say, well, why would we ever want to use simple regression when we can do multiple? Multiple is a lot more complicated, so we have to have a really good reason for using multiple. But if we're convinced that it's necessary, we can certainly do that. Sadly enough, though, that we won't have time for that here, although it is in chapter 16 in the book, if you're really that interested, or if you find that you need it in, let's say, in a class next spring and you're doing projects that involve multiple regression, then you can go ahead and look it up in this book. But for now, we'll focus our attention on simple. And when you get through it, you'll say to yourselves, well, it's a good thing that we did this because this is complicated enough as it is. Okay. Hold on a second. I just have to do one thing. I want to make sure you know that this is the version that I took notes on today. All right, that's good. All right, so what are we doing in this chapter? Well, first things first, of course, we're assuming that there's a dependent and an independent variable. Remember from travels in math that you often illustrate a relationship between two variables with the XY coordinate system. And we assume that Y is a function of X, which means that X is the so-called independent variable. Y is the dependent variable. Okay. Now, in scientific applications, let's say, for example, if we were trying to analyze the relationship between, let's say, Celsius and Fahrenheit, actually, I'm going to do it the other way around. So what we're assuming here is that F is a function of C. And furthermore, F is F and C, or let's put it this way, there is a linear relationship between the two variables. And all that means is I can draw it as a straight line. And furthermore, this is my slope, and this is my intercept. And so in other words, if you drew it out, you'd have something like that. And the intercept here would be 32. Okay, so this is what we're assuming when we start a regression analysis project of some kind. We're assuming that this type of relationship exists between the two variables that we're studying. It is a linear relationship, a straight line, and one is dependent on the other. Okay, now, unfortunately, in the real world, we often find that these relationships may be linear or roughly linear, but they're not going to be as precise as something like what you're seeing here. There can be deviations from this linear relationship. So, for example, what if we're trying to analyze the relationship between height and weight? Well, I think it's a pretty safe bet that weight depends on height. It's not the other way around. Okay, so that means weight is y and x is height. So what you would do here in order to analyze this relationship is you'd gather up a bunch of data, sample data. Okay, and what you can do then is this. In order to analyze this relationship, sample data is gathered in order to ensure that the relationship is linear, or at least approximately so. A special type of graph is constructed, which you've probably seen before, known as a scatter plot. Now, a scatter plot is basically it's actually implemented as a series of dots. So imagine yourself gathering up a bunch of volunteers for this study, and you measure their height and their weight. For each individual in the study, they will have a single point on the scatter plot. Now, for this particular case, both the dependent and independent variables are required to be non-negative. So we'll only end up needing the first quadrant of this graph. But still, you get the idea. What are we trying to show? So each one of these points is the height and weight of a single individual in my sample. And what I'm looking for is a pattern, if there is one. And just as we expect, you can see that if I drew a line through these points, which is called a trend line, there does appear to be a relationship here. In fact, you can think of it as the following: as height increases, y, or I should say weight, tends to increase as well. Now, of course, it goes both ways. I mean, if x is decreasing, if the height is decreasing, so would the weights. Okay, so if you notice too, the trend line has a positive slope. And that indicates there is a positive, or sometimes we say direct relationship between X and Y. Now, unlike the relationship, though, between Celsius and Fahrenheit, if you notice, these points, for the most part, are not actually on the line. Okay, the relationship is not perfect. It's not perfectly linear, although it does appear to be linear or close to it. Why? Well, you know perfectly well that height is not the only determinant of your weight. I'm sure you've met many very tall people who weren't all that heavy because they were very slim. And you've also met people who weren't all that tall, and yet they're still quite heavy because they were very, let's say, very muscular, and everything in between. So there's a strong connection, but it's not a perfect connection. Otherwise, all the points would be right on the line. So this is what we are up against in regression analysis. We have relationships that are pretty strong, but not perfect. And so we have to deal with a lot of uncertainty with regression analysis. But here, at the very least, we can come up with a reasonable estimate of the slope of this line. And whatever that is, will give us a good idea of how much each extra inch of height adds to a person's weight on average, and vice versa. So that's what we're trying to do. We're trying to come up with the equation of this trend line, given that the points are not perfectly all on the line. So this is a good example of what regression analysis is all about. Estimating that equation will tell us not only the direction of this relationship, but the actual numerical values of the slope and intercept. That's what we're after. All right, and by the way, in practice, we're usually not terribly interested in the intercept. It's really the slope that we're after. Okay, that's the number that really is interesting to us. Like, for example, if you're a medical researcher, you may want to understand exactly how much each extra inch of height is contributing to a person's weight. Here's a financial example. You know that if you've ever heard of it before, the Standard & Poor's 500 is a stock index that reflects the 500 largest stocks in the United States. And we see it in the news every day. There's always a mention of the Dow Jones and the Standard & Poor's 500. And so because the Standard & Poor's 500 reflects pretty much the entire economy, it stands to reason that the returns to individual stocks will be closely related to the returns to the S&P 500. Very few companies can do well when the economy isn't doing well, and vice versa. So therefore, that's why we want to maybe understand this relationship. How would we do that? Well, you would gather up data. And this time, you can assume that the returns to Apple depend on the returns to the S&P 500. Now, because these are stock returns, they can be negative. So we'll end up probably with something along these lines. Oh, let me fix that. There we go. Okay, so in other words, that line I just drew, the trend line, tells me that when the S&P 500 goes up, Apple stock tends to go up as well, or at least Apple returns tend to go up. Not because necessarily, one is causing the other. We don't want to jump to that conclusion, but what it means is that when the S&P 500 is doing well, probably the entire economy is doing well, and therefore so will Apple stock. So that's why we see something like this. So the trend line, the equation of that trend line will tell me when the S&P 500 goes up by 1%, what tends to happen to Apple stock. This is the kind of thing we see in finance all the time. You'll run into this in the spring, I think. But it's regression analysis that makes it possible for us to estimate the equation of the straight line. All right. Now, I did mention that multiple regression would mean that there's a second or third or more independent variable. Let's take a quick look at this, just because we want to know what it means. With multiple regression, there will be two or more x's, which will designate x1, x2, x3, et cetera, et cetera. And so, for example, what if an economist is studying the relationship between 90-day Treasury bill yield and the growth rate of the money supply and the growth rate of real GDP? Now, this is a hardcore economics example. You've seen this before. Treasury bills are issued by the government to raise money to cover their deficits. The interest rates that are paid on these are a benchmark in the economy. Everyone pays very close attention to them because all the rest of them are higher than that. The money supply determines ultimately interest rates and inflation rates, and real GDP is, of course, the state of the entire economy. So it stands to reason that interest rates reflect both the money supply and real GDP. And so in a case like that, in order to analyze that relationship, we're going to need to have two independent variables. Specifically, we're assuming that the Treasury bill yield, Y, depends on both the money supply growth rate, X1, and the growth rate of real GDP, which we'll call X2. Okay, but like I said, we're not going to do that one. It gets very, very messy in a hurry. And so we'll have to focus our attention on simple regression, but that's fine. Anyway, by the way, also another reason for not doing multiple regression is because the calculators are unable to do that. They're restricted to just simple regression. If we get into multiple, we would need to use software or something like that. Anyway, here's the linear regression that we're analyzing. So the word linear, of course, contains the word line. And everyone remembers that the equation of a straight line is y equals mx plus b. Which I just realized is on the next slide. And of course, m is the slope, meaning how much is y changing in response to a given change in x. B is the intercept. Oh, yes, it's all coming back, isn't it? That's right. There's certain things in math that nobody ever forgets. One of them is the equation of a straight line. So the intercept is here. The slope is sometimes written like this. It's equal to change in y in response to a change in x. Sometimes you see it written, whoops. Oh, well, here it is right here. M is equal to delta y over delta x, which in high school it may have been taught to you as the rise. I'll put that in quotes over the run. Change in y over change in x. Okay. The intercept, by the way, is simply the point where x equals 0. That's actually the point 0, comma b. Okay. Beautiful. So the scatter plot, here's an example that I did in Excel. So here's two variables that really appear to be very closely related to each other. See, it's almost a perfect relationship. I don't think we have any problems here jumping to the conclusion that these are linearly related, and regression analysis is perfectly suited for this case. What we're going to try to do is estimate the equation of this straight line. Let's compare that with this case. Ooh, now that doesn't look very linear to me. In fact, that's not linear at all. This one is said to have an exponential trend. Because if you notice, what's happening here is that as x increases, the growth rate of y is accelerating. And in fact, if you look carefully at the line, the slope is increasing. With a straight line, the slope is a constant. with something like this, the slope is actually increasing. So you see this often. You could think of this as, let's say you were trying to figure out how much money you'll have in the bank if you leave it there long enough. You'll put a bunch of money into the bank and leave it there for 20 years. Because interest is growing over time, the balance in your account will continue to grow at a progressively increasing rate, and it will closely resemble what you're seeing here. So that would mean that either we can't use linear regression at all, or else we have to make some changes. There are ways that you can adjust your data so that it can still be used for linear regression, but we're not going to cover those here. So what you would probably do is choose different variables instead of using these, because it's clearly not linear. All right, now this is where the notation starts to come. And it's going to be a little scary at first, but just keep in mind, it's basically an attempt to capture a linear relationship where we have this problem that the points are not all directly on the line. And that does require us to do something a little bit different. So just quickly remember that, as in the past, we will be, just throw this in here, when carrying out a regression or analyzing what we have to keep in mind is we are estimating a population regression line with sample data. So this part is no different than what we did in the past. For example, we know that X bar is an estimate of mu because X bar is the sample mean and mu is the population mean. So the same thing is happening here. We're assuming that in the entire population, there is a regression line that explains that relationship, but we don't have access to that much data. All we have is a sample. So we're creating a sample regression line as an estimate of the population regression line. So we do have separate notation for the sample and the population versions. We'll start with the population version. Now look at this thing. First things first, you can tell this is meant to represent the population because of all the Greek letters. Okay, so, and if you look carefully, it closely resembles a straight line, except that the intercept comes first. So this beta 0, this is the Greek letter beta, by the way. Rather than having two separate Greek letters, the tradition is to have beta 0 for the intercept and beta 1 will represent the slope. Now, here's where it gets interesting. This is the Greek letter epsilon. And it is used to represent what's called the error term. What is that doing there? All right. Well, like I was saying before, with the relationship between Fahrenheit and Celsius, there are no error terms. All the line is perfectly straight. There's no deviations from it. But when we're looking at heights and weights, for example, that's not the case. So here's your regression line. We have points that are scattered all over the place. So an error means how far off the line is the point. Okay, so like here, for example, let's call this epsilon 1. It's equal to the actual value of y minus the regression, or the estimated y on the population, on the regression line. It's wrong. In other words, the line is not perfect. It's not capturing this relationship perfectly. It's doing a pretty good job. But for each individual point, potentially there's this gap between where the point is and the actual regression line, and we call that an error term. Now, if you notice, the same thing is true up here. Let's say we call this E. All right, let's do this one, E2. Same thing. Actual Y2 minus estimated Y2. They're not the same, are they? E1 is actually different than E2. And in fact, there's no reason for any of them to be the same. So as far as our notation is concerned, let's scroll it back for a second. I want to point out that unlike a normal straight line, each of these terms is indexed, or at least the x's and the y's and the error terms are indexed, because we know that each one is likely to have a different error term. So we need to know which one is which. So a normal straight line is just something like this. Here, though, because of the potential for these error terms, we have to index the values of y, x, and epsilon, so we know which one is which. So in other words, I can make a distinction between the error term for 1 and the error term for 2. Okay, and so this point, by the way, would then be x1, y1. And this point would be x2, y2, et cetera, et cetera. So this is what's going on in the population regression line. It's starting to get scary, isn't it? Yes, don't you worry, it'll get better. But this is the challenge we're up against. The idea is that we're trying to estimate this relationship, given that it's not a perfect relationship. There are other things going on here. Now, by the way, here's an interesting question. Why are there error terms in the first place? There's a few reasons, possible reasons. Number one, y may be affected by variables other than x, and we're missing them. 2, there may be errors in the data itself. 3, some of the assumptions, which we'll discuss in a few minutes, of regression analysis are not true. So in other words, we're making assumptions that are not true. So there's 3 possible reasons why this is happening. So we just have to live with it. I mean, this is what's normal. You're never going to see a regression result where all the points are right on the line. It just doesn't happen. That's not the real world. Okay. So in the next slide, I see that I've already done this, started to do this with the weight example in heights. And you can see with all these different ordered pairs, which represent the different points in the data. And then we have an error term associated with each one. Okay. So, and by the way, some of these are positive and some of these are negative. You can see that error 4 is positive, whereas error 3 is negative. Okay, error 3 is up here. There's error 4. So that's because here the actual y for that is greater than estimated line on the regression line. Whereas here it's the other way around. Actual by 3 is less than the estimated by 3. Wow. And yes, that's why we need to have indexes so that we know which point is which, because they're all going to have different error terms. Oh my God. Don't forget, the calculator will help us with all this. What we're ultimately going to be doing here is we're going to estimate these relationships and then interpret the results. All right, now. Here's a graph, a real graph from the book that might make it easier to see what's going on. Look at those curves. You see what's happening here is that when we estimate a regression line, what we're essentially doing is we're treating each point in that line as being the center of a probability distribution. In other words, we're assuming that the error terms are normally distributed, and that it can be anywhere, like in this case. The second one here, you notice how there's a normal distribution. The center is here. And then, but all these others are possible too. So what we're trying to do is capture the center of these distributions when we construct this line. And that's because we're assuming that the error terms are normal. Right, so when we construct this model, the reason why the points scatter all over the place is because we're trying to capture the center, but the actual points could be elsewhere. So, but what is important is that each of these curves is the same. It's the same, at least I shouldn't say they're the same. Each curve has the same standard deviation. Although they do all have the different mean. If not, the shapes would be different, and that would violate the assumptions of regression analysis, and that would lead to trouble for us. That means our results would be not that accurate. All right. I have another diagram. Okay, good. So this term is the mean right there. The center of that curve that we saw. And so the entire line consists of all those means, of all those distributions. All right, let's just quickly go through the assumptions that we're making, basing this on. Number one, as we've already seen, for each x in our population, the value of epsilon is normal. It has a mean of 0 and a standard deviation of sigma. We don't know what that is unless we have the actual data, but we're assuming each xi has the same, or I guess I shouldn't say that, distribution of errors. For each xi has the same standard deviation. which we'll call sigma. So technically each one can be different, but we're assuming that they're all the same. So the shapes are the same. So if not, see, yeah, I hear it is. I did try to draw a picture of this. Let me jump ahead and show to you what it would be if the standard deviations are different. Okay, get the idea. On the one on the left, they're all the same. They're all the same shape. The one on the right, no, they don't. Okay, so we assume that the one on the left is what's happening. Now, that was the first assumption, by the way. We're assuming that the error terms are normal. The mean is 0. The standard deviation is sigma, which is the same for each one, we're assuming. By the way, the fact that we're assuming that the epsilon is 0, has a mean of 0, isn't that, it's helpful, but if you can see here, I've got two regressions going on. And the one on the left clearly is a very good regression. This is a case where X really does help explain Y. You can see X is sales and Y is profits. How do you know? Because the points are very, very close to that line. So on average, the error terms are 0. In other words, the ones above the line cancel out or average out to 0 with the ones below the line. Now that's true of the one on the right too. This is a silly regression, by the way. We've got profits against temperature, which really there's no connection there, but that's the reason why these points are so far off the line. But they do cancel each other out. In other words, the average of these ones above the line and below the line are 0, but the standard deviation is quite high. So you can see the one on the left, we can have a lot of confidence in our results. The one on the right, not so much. So that's what the error terms are really capturing. How close are these points to the line? And how large are their standard deviations? Okay, the one on the left has very low standard deviations. The one on the right, they're very high. So even if they're all equal to each other, they're still very low on the left and high on the right. With the most confidence in our results when those standard deviations are low. And thirdly, we're assuming the error terms are independent of each other. They don't affect each other. Now, let me show you, I'm going to do another graph where you can see what would be the case if that wasn't true. All right. Give me a minute to catch up. All right. So let me draw another set of graphs. So on the left, the error terms are independent of each other. How do you know that? Because there's no pattern there. Sometimes the points are above the line, sometimes they're below. Over here, though, watch what happens. So if you notice, we have here all positive error terms. Then suddenly we have all negative error terms. What this is saying is that when there's a positive error, there's a strong tendency for there to be another positive error. When there's a negative error term, there's a strong tendency for there to be another one. So even if they do average out to zero, as they're supposed to, there's a pattern there. And that's going to be a problem for us. So we're assuming that the case on the left is the one that we actually see. If not, we have to do something about it. There are corrective steps that we can take, although we won't be doing them here. And but we need to know that this is a problem right away before we do any calculations. So here, there's no pattern to the errors. On the right, there's definitely a pattern. All right. Now, what we're actually doing here, there's many different kinds of regression models that we could use. We're going to use something called ordinary least squares. This is the simplest version of it, of regression analysis, but it's also the most popular. The problem with it is that it's the most dependent on our assumptions. So the trade-off is that it's easier to use than the others, but it also is more affected by the assumptions. What this is all about is how exactly do we estimate our regression line, given all this information we have, all these points scattered around. How do we come up with a line that best captures that relationship? Okay. And when you come and think about it, I mean, there's a lot of ways we could do this. Let's say, for example, we have some data. We have our scatter plot. We're trying to capture or create a trend line that gets really close to the data. So clearly, visually, we're looking for something like this. But where did that come from? This trend line is estimated using what's called ordinary least squares, or OLS. Okay, that's the one we want. Now, what if we end up with this one? Oh no, we don't like that one. Oh, we don't like this one. It's the one here in the middle that clearly is the best because it captures the points better than the others. But even then, you have to ask yourself, mathematically, how was this done? What exactly are they doing to come up with this line? Good question. So first, let's introduce, though, before we talk about that, the equation for the sample regression line that we're actually estimating. So remember, we did say before that we have a population regression line. So just recall, the population regression line looks like this. Corresponding sample regression, which is what we're going to estimate. looks like this. Oh, now that's different, isn't it? It is quite different. What's going on here? Well, for the obvious ones are the B's versus the betas. Now remember, this is the sample regression line. We're using the Roman alphabet. So B0 is an estimate of beta 0. B1 is an estimate of beta 1. Y, now this is called Y hat, very informally. The symbol is called the caret. Whenever you see that caret in statistics, it means that we're estimating something. This is an estimate of Y. Now, if you notice, there doesn't seem to be an error term here. There's a reason for that. That's because on average it equals 0, so it drops out of the equation. So we're left with this. This is when we run a regression on our calculators, this is what we're going to get out of it right here. So it's pretty straightforward. It looks more like a straight line. Okay, so that's where we're going with this. Now, even though it's not in the equation, just want to mention here that epsilon is a Greek letter. It is the population error term. Even though it is equal to 0 on average, we do have an equivalent for the sample called EI instead of epsilon I. And instead of calling it an error term, we call it a residual. That's going to play a key role in our estimation of this equation. So E is being used to replace epsilon for our sample population, sample regression line. Wow. Yes, it seems like a lot, doesn't it? And it is. But this is just background. What we'll be actually doing is estimating the regression line and analyzing the results. So all of this scary stuff is really just terminology. And we're not going to focus so much on this, but on actually running the equations and figuring out what the results are telling us. Anyway, so let's take a look at this graph. Help us get a feel for what a residual is. Here's a given point, X and Y. See that it is above the regression line that we're estimating. This is now the sample regression line. You notice its equation over here. The gap between the actual value of Y and the value estimated from the regression equation here is known as a residual. And here the residual is positive because the actual Y is greater than the expected or average or estimated Y. And formally, it's written like this. Okay, so we would want, ideally, those residuals to be as small as possible, wouldn't we? Yes, we would. Okay. So the point of all of this is that the equation that we estimate, this one right here, was calculated by minimizing the sizes of these residuals. Okay. That makes sense, doesn't it? You're trying to get as close as possible to all the points. So what you're trying to do is minimize these residuals. And the one unique formula that does this is what will be used as our sample regression line. Now, unfortunately, if our assumptions are correct, though, on average, residuals will add up to 0. So what do we do about it? We're going to actually minimize the sum of the squared residuals. So this is the OLS technique. Slope and the intercept are estimated by minimizing the sum of the squared residuals. All right. And when we're done, by the way, later on, you'll see there's formulas in the next section, which are the result of doing this. And we'll see the actual formulas that are being used to estimate this regression line. We won't have to use it because we'll let the calculator do it. So this diagram, this is something similar to what I was showing you earlier. You can see that with these points, there's 2 lines here, and you can clearly see one is better than the other. And so the one that we're going to keep is, of course, A, because here, sum of the squared residuals is the smallest. Wow. All right. Now, all of that was what we call 15A. There's 2 more sections of this. But don't you worry. Next session, we'll get our hands on the calculators. And all of this background will be important, but maybe not quite as important. So don't be too panicky. It looks like a nightmare, but once we start using the calculator, you'll see it's very straightforward. And I'm also going to introduce to you some Excel so you can see how it handles these same types of problems and how what kind of information it gives you. So anyway, this may not have been the best time to do this chapter just before Thanksgiving, but like I said, this is just background. Calculator will do a lot of this for us. So I think we might as well stop right here, and I'll see you all after Thanksgiving break. Okay.
Thank you.
All right. See you next week.
Thank you.
Thank you.
Thank you, Professor.
Bye. Thank you.
See you later.